Николай Константинович, прошу прощения, пока не началась лекция, можно спросить, предыдущие домашние задания вы все уже проверили или нет? Просто нет оценки у меня никакой. Николай Константинович, прошу прощения, меня слышно? Николай Константинович, прошу прощения, меня слышно?
Да.
Хотела задать, пока лекция не началась, вопрос. Все предыдущие домашние задания уже проверены? Я просто отправляла, а у меня оценка не стоит, и вообще в списке меня нет.
Ох,
Комиссарова Полина.
ничего, нет, не все. Не все. Сейчас я посмотрю. Конкретно ваша, я думаю, не проверена как раз. Я их ничего не успел сделать. Сейчас, одну секунду. Ну да, ваша не проверена. Да, извиняюсь.
Ничего, спасибо большое.
Так, ну, в общем, в любом случае, лекцию надо начинать уже. Окей. Let's see what we have for today. As I understand, we need first to describe an efficient algorithm to decode from errors for the Reed-Solomon code. So recall that, what is the Reed-Solomon code?
Извините, там люди ждут, что вы их пустите в конференцию в некотором количестве.
Ух ты. Сейчас. Сейчас, почему я их не могу пустить? Интересно. Может, потому что... понял. Адмитон. Так, кстати, а еще нужно посмотреть, нет ли тех, кто по старому адресу зашел. Сейчас. Тоже важная вещь. Так, никого там. Нет, есть. Двое. Так, значит, мы переехали на Zoom. Сейчас я кину ссылку вам. Значит, вы можете просто посмотреть на сайте. Сейчас я вам попробую ее просто скинуть. Там, где она у меня. Ага. Здесь. Так. Сейчас видите ссылку? Давайте покидайте тогда, идите туда. Ага. То и сейчас. Ладно, я пока закрывать не буду. Хорошо, окей. Let's admit.
Пока мы еще не начали.
Да.
Я сказал вам домашнюю неделю назад, в пятницу прошлую, а в таблице себя не увидел.
Ну да, я половину не проверил еще. Ну, точнее, так, мы вдвоем проверяем с Сашей Казачинским. Свою половину он сделал, а я свою еще нет.
Ага. Я просто хочу уточнить. Вот в прошлую пятницу вы говорили, что можно до полуночи скидывать, да? Дедлайн был в пятницу.
Ну, допустим. А что вы хотите спросить?
Да, я просто боюсь, что вот мало ли не засчитали мне или что-нибудь.
Нет.
Ага.
Я все засчитал, да, до полуночи. Да.
Хорошо,
Так.
Спасибо большое.
Ну ладно, давайте начинать лекцию.
Я прошу прощения, можно еще раз? Мы только до полуночи скидываем, то есть сегодня нельзя было уже присылать?
Почему? Вот по полуночи еще нельзя.
До полуночи текущего дня.
Ну да.
Прошу прощения, все, простите.
Ага. Так. Значит, так, там нет никого. Надо думать, что все уже поняли, куда надо идти. Хорошо. Read Solomon Codes. So let's use the Blackboard of the last class. So for Read Solomon Codes, it has parameter n and k. N is the block length, k is the message length, and the distance is n plus 1 minus k. The alphabet, the cardinality of alphabet should be a power of prime, so that we can establish a field structure on our alphabet. The messages are polynomials of degree k minus 1. So each polynomial is identified by k coefficients, which are considered as letters. So the length of messages is k. And every message is encoded by the value of the respective polynomial in some fixed n points. So we need that the block length n is less than or equal to q, so that there are indeed n distinct points. And we have proved that indeed the minimal distance of this code is n plus 1 minus k. The parameters of the codes are n, k, and q, may be chosen arbitrarily with the following constraints again, that n is at most q, and of course k is at most n. And we have considered, the encoding is very easy for this code, because we just need to compute the value of the given polynomial in the given points. The decoding is also easy, assuming that we have no errors. So knowing the value of the polynomial, we can reconstruct its coefficients, and to reconstruct them, it is enough k values. And either we can use Lagrange polynomials to this end, or we can solve the system of linear equations. But now we will consider a more delicate problem, decoding from errors. That means that now we have the values of our polynomials, but some of them are wrong, and we don't know how many of them. So the theory says that we can decode from E, which is equal to d minus 1 over 2, and we need to take the floor of that, which in our case is equal to n minus k over 2 errors. So that means that up to these values in our polynomial, in our table, are wrong. And of course, we can do that using the brute force search. We can consider all possible messages and encode all of them and find out which of the code words we obtain is a distance at most E from the table we have, from the corrupted table we have. But this is very inefficient. So this will be an exponential time algorithm. And in practice, we can't use such a non-efficient algorithm. And now I will explain how to do that in polynomial time, assuming that we do not charge for field operation. Field operation I assume to perform in so to say 1 unit time. And actually this is a very right assumption, because indeed we can represent any finite field in such a way that field operations can be performed efficiently. So the algorithm will be the following one. So first of all, let's denote the initial polynomial by, it is unknown to us, by p of x. And the function we receive by tilde, so of x. So we will assume that our input, the input to our algorithm, is tilde p of x1 and tilde p of x2, and so on. So these are the corrupted values, but we know that at most E of them are wrong. Other values are equal to P of xi. So this is our input, and the output should be the coefficients of the polynomial. So how to do that? And the idea is we will use similar idea as in the second decoding algorithm. We will use linear algebra, and we will solve some system of equations, linear equations, and that system will provide somehow the coefficients of that polynomial. So let's start with the following easy observation. So first of all, let's stress that this is unknown. So the initial polynomial is unknown, and also the table of its values is unknown, and the input is some n field elements. So we will start with the following simple observation. Assume that x, I1, and so on are all the corrupted values. So assume that these are bad points in which the value of p is different from tilde p of x, I. If the number of bad points is less than e, just add any points to those. So we'll assume that there are exactly E of them. Consider the polynomial which is the product of x minus x1, xy1, and so on. This polynomial vanishes in all bad points, in all the bad points. And its degree is E. So now assume that we multiply the function tilde p by that polynomial. We obtain some function. And the values of that function in all the n points is the same as the value of the initial polynomial times that annihilator of errors, q of x I, for all i's. For all, that's important that it holds for all I from 1 through n. And why is this? Because if xi is a bad point, then we know that both values, the left-hand side value and the right-hand side value, are zeros. And otherwise, they are the same because tilde p and p is the same. So this equality holds for all points. Now, observe that this is the polynomial of degree k minus 1 plus e. So the degree of this polynomial is k minus 1 plus e. And so, and the degree of q is e. So we actually have proved that there are two polynomials. One of them is denoted by q. We know that its leading coefficient is 1 and its degree is e. The other one is degree k minus 1 plus e polynomial. We will call it r. And they have the following property, that tilde p times q and r have the same values in all I points. So we have proven the following lemma. Of course, we can't find such q and r directly because to find q, we need to know which points are bad and which are good. But lemma will state just that there are such polynomials, maybe different from q and our q and r, different from those q and r we have constructed. So there are degree e polynomial, degree e polynomial q with leading coefficient 1. And there is a degree k minus 1 plus e. Here, this means that its degree is at most this value. It might be strictly less than this. R such that r of xi is equal to tilde p of xi times q of xi for all I. Now, the first step of the algorithm will be to find any such R and Q. So we can't find the annihilator of bad points, but we can find some Q and some R satisfying the following this property. So this will be the first step of our algorithm. Step 1, find such Q and R, such polynomials Q and R, any such. To any polynomials Q and R satisfying lemma 1. Satisfying lemma 1. And how we can find such Q and R efficiently. So let's see again, what do we want? We want, we have n constraints. For each xi, we have the constraint that the value of r in xi is equal to some specific number given to us. We have received it from our channel, times the value of q in xi. Notice that if we consider the coefficients of polynomials r and q as variables, this is a linear constraint. So one coefficient of q is fixed, the other one, the leading coefficient is fixed to 1. The remaining coefficients are unknowns, and this is a linear inequality in our unknowns, which is easy to see. For example, if we take, say, a polynomial a0 plus a1x plus, say, a2x squared, and evaluate it in some point, say, x equals to 1, we will obtain just a0 plus 2a1 plus 4a2. So for every specific point xi, if we consider the value of polynomial, unknown polynomial at that point, is a linear combination of its coefficients. So we have here n linear equalities, and we know that that system of equalities has a solution because lemma states that there are such Q and R. And we can find some solution just using the linear algebra as we did when we have considered the second algorithm for decoding without errors. So just use Gaussian elimination algorithm, for example. So this is done on step 1, and step 1 can be done in polynomial time. So now we assume that we have already such Q and R, and lemma 2 states that actually it must be that Q and R have the following property, that P times, the P is the polynomial we are looking for, the initial message. P times Q must be equal to R. So let's prove lemma 2 now. So let's see first what we know about degree of those polynomials. So by construction, the degree of R is k minus 1 plus e, plus the maximal number of errors. what is the degree of this polynomial in the hand side? It has the same degree. Degree also, because the degree of P is k minus 1, and degree of Q is E. So we have to show that two degree k minus 1 plus E polynomials coincide. Linear algebra tells us that to this end, it's enough to show that they coincide in their values coincide in more than k minus 1 plus E points, because any two polynomials, any non-zero polynomial, any degree D polynomial, if it has D plus 1 roots, then it is 0. So let's see in how many points they have the same values. We know that R of xi is always equal to P tilde P of xi times Q of xi. This is true for all the n points, our chosen points. But now we also know that tilde P is the same as P, but not always. This is true for n minus E points, because the total number of points is n, and the number of bad points is E. So the second equality is true for n minus I points. So conclusion, R and PQ have the same, take the same value in n minus I points. So it's enough to show that n minus I E is at least the degree plus 1. K minus 1 plus E plus 1. The degree of those polynomials plus 1, which is K minus E. So it's enough to verify that n minus E is at least K minus, K plus E, sorry. K plus E. That is that n minus K is larger than or equal to K plus 2E. Sorry, 2E, 2 times E. But this is, we know this exact because by definition, E is 1/2 of n minus K. Recall that E is equal to n minus K over 2. We have to decode from that many errors only. So we know this in advance, and so the second lemma now is proved now. So now we see what should be the second step. The second step is to divide the polynomials we have found R by Q. So step 2, divide R by Q using some algorithm. There is a school algorithm called long division algorithm. По-русски это деление уголком. Полиномы можно, как и числа, делить уголком. So long division algorithm. So this algorithm runs in polynomial time. And we will obtain the quotient, which is P, and the remainder, which is 0, because R is divisible by Q. And so on the second step, we find the message we were looking for that finishes the theorem. Так, есть вопросы по доказательству? Are there any questions?
Нет.
Что-то я в чате не вижу.
Все понятно.
Ну, вроде да. Okay, good. So we have described now how to decode from errors for Reed-Solomon code. And as you recall that Reed-Solomon code is the perfect code. Its parameter can't be improved, meaning for fixed Q and N, we can't, and D, we can't make K smaller, or for fixed N, K, and Q, we can't make D smaller. And now I will proceed to another famous perfect code, which is called the Hamming code. The Hamming code has also that property that it's perfect. We can't improve its parameters because its parameters lie on the volume bound. So the parameters of Hamming codes, so every Hamming code is defined by one parameter, which is a natural number. And in that code, the block length is 2 to that parameter, call it, say, m minus 1. The dimension, that is the message of length, is 2 to the m minus 1 minus m. So m bits less than the block length. So the difference is only m between the block length and message length. That is that the rate is close to 1, but the distance is very small. It's only 3. So that code corrects only one error, and the alphabet is binary. And this is the codes are all also based on the linear algebra. They are linear codes in a sense. Later I will specify exactly what does it mean being a linear code. But up to now, let's consider the field of two elements, 0 and 1. They are added and multiplied as usual. 1 plus 1 is 0. And as I have said, they are perfect in the following sense. The volume bound for that code specifies to equality, so it is attained. Indeed, the volume bound says that the volume of the d minus 1 radius ball, that is 1, d minus 1 over 2 is 1, times 2 to the dimension, 2 to the k, is at most 2 to the n. In our case, the volume of the ball is n plus 1. So in our case, the volume bound says the following inequality, and actually n plus 1 is 2 to the m. In our case, 2 to the m times 2 to the k is at most 2 to the n. And by definition, m plus k, if we add the dimension and m, we exactly obtain n. So in our case, all these inequalities are equalities. that is, the code is perfect. So how to construct such a code for any given M? The code is constructed using a system of linear equations. So the set of code words will be the set of all solutions to a system of linear equations. Usually in the theory of, in the coding theory, this matrix is called parity check matrix. Parity check matrix. In the binary case, it's one can understand why we use parity check. So these words, because the number of columns in this matrix is equal to the block length. So the code words are solution to the system of equations, and each row of that matrix actually means that some parity, the parity of some subset of bits of the code word is 0. So the parity check matrix is the matrix of the system of linear homogeneous equation. So we multiply this by x1, xn, and it should be equal to 0, 0, 0. So this matrix is considered a system of linear equations, linear homogeneous equations. And in the case of Hamming codes, that matrix will have m rows. So we will have m equations and n variables. So the dimension of the set of solutions will be 2 to the m minus 1, n minus m, as we wanted. So now let's just specify what will be the parity check matrix for this particular code. We just list its columns are all different non-zero vectors of height m. So for example, in the case for m equal to 3, we will obtain 7 non-zero vectors. 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, and all 0 vector. So there are 7 of them. In general case, there are 2 to the m minus 1 such columns, and the number, the height of the column is m. So this will be the parity check matrix of the Hamming code with those parameters. So what do we need to verify? First of all, that the number of code words is equal to 2 to the m minus 1 minus m. This is because the dimension of the space of solutions to this system of equations is exactly equal to the number of variables minus m, because this is matrix has a identity submatrix. This one, the first m columns form an identity submatrix, and so it's not degenerate matrix. So its rank is exactly m, the number of rows. And so the set of solutions has exactly dimension 2 to the m minus 1 minus m. And So we can choose some E1, E, K, where K is that number 2 to the m minus 1 minus m. Vectors as a basis, and our code words will be all possible linear combinations of those K vectors. Each lambda can be chosen in two ways, either 0 and 1. So in total, we have 2 to the K, the number of choices for lambdas, 2 to the K vectors which are solutions to that system. So we will have exactly that much code words. So we have verified these and these parameters, and it remains to show that their minimal distance is 3. So we need to show that any two vectors differ in at most, any two code words differ in at most 3 positions. So, and this is very easy. So if X and Y are code words, then the distance between them is at least 3. And this is done as follows. We will use the notion of the Hamming weight. So the Hamming weight between some Z is denoted as absolute value of Z is the number of non-zero symbols in Z. So in other words, this is a distance from Z and all 0 words. So if X is different from Y, then X minus Y is definitely non-zero. And the distance between X and Y is the same as the distance between X minus Y and 0, because all the symbols in which X and Y differ provide a non-zero symbol of X minus Y and the other way around. So this is the same as a Hamming vector, Hamming weight of X minus Y. So we need to prove that if Z is a solution to our system, actually, because our system is a system of linear equation, X minus Y is also a code word. So we need only to show that if Z is a code word and non-zero, then its Hamming weight is at least 3. So let's see why is this. First of all, it's impossible that some solution to this system has Hamming weight 1, because if it has Hamming weight 1, that means that if we multiply this matrix by that vector, we obtain some column. Hamming weight 1 means that it has exactly 1, 1, and the remaining bits are 0. So multiplying by such a vector just singles out some a column of that matrix, and all the columns are non-zero. So it's clear that there are no solutions of Hamming weight 1. And also there are no solutions of Hamming weight 2, because assume that we have only 2 ones, say this one and this one. When we multiply our matrix by such a vector, we will obtain the sum of two different columns. But all the columns are different. And so their sum is non-zero. Here we use that all the columns in our matrix are different. So there are no solutions of Hemingway 2. And that's it. Actually, there are solutions of Hemingway 3. It's, for example, if we take this column and that column, their sum is 0. That means that we have a solution with Hemingway 3. So the minimum distance of our code is exactly 3. So we have proven our lemma. And it remains to explain how to encode and decode from errors for that code. Let's see how we can encode. So we have messages of length k, which is 2 to the m minus 1 minus m. And to encode, we can use the following feature of our matrix again. Our matrix has a identity submatrix, this one. So that means that it can be represented as follows. The identity matrix times the first. So the system can be represented in the following way. Identity matrix times the first m variables plus some matrix, call it A, say, times the remaining variables, xm plus 1, xm to the m minus 1. And so we see, and the code words are obtained as solutions to that system of equations. So that system, because the product of identity matrix and some vector is just equal to that vector, this actually means that the first m variables can be expressed through the remaining variables. And using this feature of our system, we can encode very easily. So the height of this column is exactly equal to the dimension. So we can consider these bits as messages bits. So the encoding will be as the following. We take our k bit message, multiply it by matrix minus A, and obtain the remaining m bits. And this will be the encoding of our message. So the encoding will be performed just by multiplying by this matrix and then taking the negative sign.
May I ask a question?
Da, yes.
So should we say that we should multiply by matrix minus A, because we are working in F2 field, so minus A equals to A.
No, it's the same as A, right? Right.
Okay.
We can put here plus sign anyway. Indeed. Okay, so the encoding is very easy, and the decoding from errors is also very easy. So what means decoding from errors? We receive some x tilde 1, x tilde n bits, and we know that some of them, say this one, is corrupted. So it's different from xi, and the remaining are equal. And we need to find which one is wrong. We need to find I. To this end, we just compute what we obtain if we multiply our matrix, parity check matrix, by this corrupted vector. We will obtain some m bits. And call it B1, BM. Now we see that actually this vector is one of our vector inside our matrix. And if we change that bit in our tilde x1, tilde xm, if we change such a bit, then that product will be changed by exactly that vector. So it becomes 0. So we understand, looking at this vector, we understand which bit of our corrupted message tilde x should be changed, flipped, so that to obtain a solution to the system. Usually this is called the syndrome vector. So, and the entire algorithm is usually spelled as follows. First, we find the syndrome vector. Then we find in our Perichet matrix the place, the column, which is equal to the syndrome vector. And the number of that column is the wrong bit. If the syndrome vector is 0, then that means that there is no error. All the bits are good. And otherwise, we know the number of the corrupted bits. So that's it. Так, все понятно было?
Да.
Good. That's good. Now, let's proceed further. Up to now, we had two particular families of codes. Reed-Solomon codes and Hamming codes. And for both families, the cardinality of alphabet was the power of a prime, and we used the linear algebra. Actually, we used the field of Q elements. So this is the most common thing in the coding theory. Most of the particular codes are linear codes. So let's say that explicitly. What does it mean? So the linear codes means that the alphabet is a field, has a field structure, and the set of code words is a subspace of fq to the n. So C is the set of code words is a subset, is considered as a subset of fq to the n, and it should be a linear subset, a linear subspace. Which naturally means that the sum of all of two code words is again a code word. And if we multiply a code word by a field element, we obtain another code word, as usual. And indeed, Hamming codes are form a linear subspace because they are defined as a system of as a set of solution to a homogeneous system of equations. So linear algebra tells us that any such set is a linear subset. And for Reed-Solomon codes, we also had that code words are table of values of polynomials. And if we add two code words, we certainly obtain a table of a polynomial which is the sum of the given polynomial polynomials, and the sum of degree k minus 1 polynomial is again a degree k minus 1 polynomial. And also if you multiply a polynomial by a field element, we obtain another polynomial. So if you multiply a table by some value, some field element, we obtain the table of a polynomial, which is obtained by multiplying the initial polynomial by the same values. So these were indeed examples of linear codes. And now we will show that for linear codes, we have also a similar sufficient conditions as we had in general case. Moreover, it holds with it's a little bit stronger. It's called the Warshamov-Hilbert bound. Similar to Gilbert bound, but Warshamov-Hilbert bound. So it states the following. Assume that we assume that Q is a power of prime. So assume that the volume of the ball of radius d minus 1 times Q to the K minus 1. So the difference between Gilbert bounds is that in Gilbert bound, we didn't subtract minus 1. So the bound, Warshamov-Hilbert bound is a little bit, the sufficient condition is a little bit weaker, is less than Q to the N. Then there is a linear code with the parameters N, K, D, Q. And to prove this, we again will use the following observation that the Hamming weight, the distance between x and y is the same as the Hamming weight of their difference, x minus y. So that means that for, if we want to ensure that our code, linear code, has minimal length d, we just need to show that all the non-zero code words have Hamming weight at least d, because if x and y are code words, then x minus y is also a code word. So having minimum distance at least d is equivalent to saying that d of z, Hamming weight of z is at least d for all non-zero code words. Of course, this is not true in general case, but for linear codes, this is certainly true. And so we will only take into account the Hamming weight of non-zero codes. Now we will construct such a code by a greedy algorithm, but this time we will choose by using a greedy algorithm, not the code words, but the basis in the set of code words. So the set of code words is a linear subset. Now we will represent that linear subset using some its basis, not the parity check matrix. And we will denote that basis, say, by x1, xk. So we will choose greedily x1, x2, and so on, xk, such that this holds. That means any non-trivial linear combination such that the Hamming weight of any non-trivial there, Hamming weight of any there non-trivial linear combination is at least D, such that for any non-trivial means that at least one coefficient is non-zero, trivial linear combination. Z equal to lambda 1 x1 plus lambda k xk, we have that the Hamming weight of that linear combination is at least D. So this is our goal, to choose such a x1, xk. And by the way, this ensures that they are linear independent, because otherwise there would be a non-trivial linear combination which is zero. That means of Hamming weight 0. So this is our goal, and choosing greedily means that we will choose x1, then x2, and so on. And what do we need when we choose xi? We need actually the following property. Let's state it as a lemma. Assume that, I'm sorry, we will keep the following invariant true, that when we have already chosen xi and x1, x2, and so on up to xi, then any non-trivial there linear combination has the property. So the invariant we keep is the same property, but not for the entire set, but for its subset. So let's just change here k by some I and say that we want this be true also for subset. Of course, this is this is the same, requiring this for subset and for entire set, but in our algorithm, it's important that we will ensure this for subsets step by step. So call it, say this environment, call it star, this assertion. So assume that x1, xa are already chosen and satisfy this invariant. star. Then xi, x1, xi, and xy plus 1. So we add some xy plus 1 to those set of vectors. Satisfy star infinitely if xi plus 1 doesn't belong to any ball of radius d minus 1 with the center in some linear combination of the previous vectors. Here we consider all the linear combinations, including the trivial one. So the lemma says that as the new vector xi plus 1, we can choose any vector that is outside some balls. Let's see why this is true. So one implication is obvious. So if the invariant holds for the system of vectors x x1, xi plus 1, then of course it is impossible that the distance between xy plus 1 and some linear combination is small. Because if such distance is small, then also the distance between 0 and the vector which is obtained as a difference of those vectors, minus x y plus 1 plus that linear combination, is also small, less than d. If this is less than d, then this is also less than d because these are the same values. Which means that the Hamming weight of this non-trivial linear combination, it is non-trivial because we have -1 coefficient with xi plus 1, is less than d. So this direction is easier. And the other direction can be proven as follows. So assume that we know that xi plus 1 is outside all those balls. Assume that the distance between 0 and some non-trivial linear combination, which is the same as Hamming weight of that linear combination, is less than d. So assume this assumption. Then we know that that coefficient is non-zero because of our environment. Then lambda I plus 1 is non-zero, because otherwise the invariant wouldn't hold, which means that the distance between 0 and the vector lambda 1 over lambda I plus 1 plus x1 plus lambda I over lambda I plus 1 times xi plus xi plus 1 is also small, is less than d. And then we can move this here to see that the distance between xi plus 1 and minus this guy, lambda 1 over lambda I plus 1, x1 plus blah, 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 is also less than d. So this proves the other direction, assuming that the Hamming weight of such vector, some non-trivial combination less than d, we prove that xi plus 1 is inside the Hamming ball of radius less than d, of radius d minus 1, centered at some linear combination of the previous vectors. So this is the same. Lemma is proved. Now let's go back to our greedy algorithm. So by our lemma, each time we choose a new vector, we need to satisfy our lemma. That is, we need to choose xi plus 1 outside all those balls. But let's count how many balls we have. If we choose xi plus 1, we have q to the I linear combination. So xi plus 1 must avoid q to the I balls, each of cardinality, each of them has at most v of q d minus 1 elements. So the new vector should be outside some set of cardinality q, at most q to the I times the volume of the ball. And if this is less than the total number of strings we can choose from, then certainly we are able to choose xi plus 1 using that greedy algorithm. And the maximal possible I is equal to k minus 1. And even in that case, the amount of strings to avoid is less than q to the n. So we still can choose even the last kth vector in our basis. And so we see that our sufficient condition ensures that we can greedily choose up to k vectors to keep our invariant. That means to construct our linear code. Так, ну вот теорема доказана. Какие-нибудь вопросы? Are there any questions?
То есть мы начинаем строить базис с одного элемента, потом подбираем к нему еще один,
Да,
который лежит вне шара и так далее, да?
да.
Все понятно, хорошо.
Так, всем все понятно? Ну, хорошо. Значит, я вам обещал, что я буду тесты давать. Вот я сегодня... Будет первый тест. Значит, сейчас я вам скину на него ссылку, а вы его онлайн будете, значит, это самое, сдавать. Так, давайте я стоп-шер сделаю, потому что этого не нужно. Я в чат его скину.
Можно уточнить, какие у нас ограничения по времени на выполнение теста будут?
10 минут. Но, впрочем, знаете, сегодня, поскольку я вам больше дам, я даже дам 15, на самом деле вам хватит и 5, ну, вы сейчас сами увидите. Но, в принципе, я таймер на 15 включу даже, потому что я раньше закончил, чем предполагал.
Какой чат вы скинули?
Что?
Какой чат вы скинули?
Я еще не скинул, я только это самое. Его даже еще, мне надо сейчас его открыть для начала в себе. Так. Сейчас вспомню, что еще делать. Одну секунду. Ага. Вот я в обычный чат этого самого нашего конференции скинул. Вот. Значит, сейчас у нас 16 минут. Но давайте я вам даю 15 минут, значит, до 31 минуты. В 31 минуту я закончу.
Правда, что мы имя, фамилию на русском заполняем, да?
Лучше на русском. Я все ведомости хочу на русском, чтобы у меня были, чтобы не было на всякий случай путаницы.
А если закончил тест, то можно выходить,
Да, все, конечно, до свидания.
Ага. А
Только
вы
подождите-ка. Как ваша фамилия?
что вы это
Да, все, я получил ваш ответ.
получили, да? Все, хорошо,
Да,
здорово.
да.
До свидания.
До свидания.
А можно даже уточнить, комиссаровый ответ пришел?
Да,
Большое спасибо. До свидания.
до свидания. Так, осталась минута.
Простите, а от Кира Косяна пришел?
Да,
Мгм. Хорошо, до свидания,
до
спасибо.
свидания. Тридцать секунд осталось. Так, 10, 9, 8, 7, 6, 5, 4, 3, 2, стоп. Все, до свидания, всего хорошего.
До свидания.
До свидания.
До свидания, спасибо.